I want to look at one final type of exercise, and that is involving carbon dating. So I'm sure you've heard of carbon-14 dating or carbon dating as a tool to age fossils. The way that we can do that is using this formula, n equals n naught times e to the 0.00 blah 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 t. And what this does is it describes the relationship between n, which is the amount of carbon in a sample after t years, if there was a certain amount n sub 0 originally. So this requires a little bit of guesswork. So if we have a fossil that contains 10 grams right now, we might make an educated guess and assume that there were 1,000 grams of carbon-14 initially. Now this will allow us to figure out how long this piece of ancient history has been sitting around, find the age of the fossil. So the formula that relates these two things is that one up above, n. We know n is our current value. We're in the future relative to the initial start of this problem. So if n is equal to 10 grams, and n sub 0, the initial amount we think was equal to 1,000 grams, we can kind of omit the units. If they're the same units, we can say that they're related in this way. So our setup, we have 10 equal to 1,000 times e to this long decimal. That's 0 and 0, 0, 0, 1, 2, 0, 9, 4, 2 times t. Then we should hopefully be able to solve that equation for t. And there's only one unknown there, and that's t, so we're in good shape. And I'm noticing that there is actually an error in this formula. I will be updating the notes, but the equation for carbon dating is actually n equals n sub 0, n naught, e to the negative 0.0001209, etc. Sorry, that's a 4 to t, so that should have a negative out in front of the exponent. Let's put that in there. Alright, that will fix our results in the long run. So setting this all up, we have an exercise where we're told that a fossil sample contains 10 grams of carbon-14, and we assume that the original contained 1,000 grams of carbon-14. We're going to find the age of the fossil algebraically using what we know about the relationship between these two things over time. So if we have n and n naught, first off we need to know which one is which. Well, n is the current amount. N naught is the past amount, the initial amount when this object first started decaying. So our setup here, where we have n and n naught, where n is 10 grams, and n naught is 1,000 grams. We then know that we have 10 equal to 1,000 times e to that crazy long exponent. And I'll abbreviate that. Alright, now we've got an exponential equation set up here. We want to isolate e and its power. So, what should we do? Well, the only problem right now is that 1,000, so if we divide both sides by 1,000, our equation would look a little bit better. 1,000. Now the nice thing about dividing by 1,000 and having 10 initially is that the left-hand side gets very simple. That's just 0.01. And on the right, we've got e to the negative 0.00 blah 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 t. So we're in good shape. We've got the exponential part by itself, and now if I log both sides with an appropriate base, in this case we'll choose base e, we'll end up with a nice number on the left side, 0.01 in the logarithm, and the log function and the exponential function cancel each other out, and we just get the big weird exponent. And I'll start writing the whole thing now, 0.000 120.942 t and now we've got t out in the real world where it's most useful if we divide both sides by everything that's not t, namely negative 0.000120942, we'll get t by itself. We'll get t exactly. So getting that cancellation, we have a value for t, an exact value. T is equal to the natural log of 0.01 divided by that large number, negative 0.000120942. Now, having some intuition about those numbers, again, is a good idea. Whether we, when we get to the end of this, it doesn't really matter if we can look at this stuff and tell what that's equal to. What's important is that we can have an educated guess about the answer based on the original problem. So if you have a sample and it goes from 1,000 grams of carbon-14 to 10 grams of carbon-14, presumably that's going to be a positive number of years. I don't know exactly how many years, but if we set this all up, we'll have the natural log of 0.01, which will divide by that long 0.000120942, and come up with 38,077, or if we round up, we'll get 78 years. Now, we usually use carbon dating to date things that are very old, so coming up with something like 38,078 years would feel kind of reasonable. So those are all of the new applications of exponentials and logs and situations in the real world where you would need to apply some of the stuff we've learned about solving equations involving logs and exponents. Go ahead and give those homework problems a try and bring any questions you have to class.